Okay, so with lesson 8.1b, we are going to continue on with our quadratics. And we're going to take a look, and we're going to look at a little bit of a different function than what we looked at yesterday. So as you can see, today we have parentheses around our term, and we're squaring the entire thing. So what that means is that this a right here is being applied to the x input. What that's going to do is manipulate your graph on the horizontal um, grid instead of the vertical like you did yesterday. So I'm going to talk about this for just a minute, and then we're going to look at a picture excuse me, and kind of look at what the differences must be. So when you are graphing f of x equals a times x squared, the whole thing is squared, we're looking at a horizontal stretch and a horizontal shrink. So yesterday we had our vertical goggles, as we're going to call them. We had our vertical goggles on, and we were looking at being stretched and shrunk or compressed going up and down. Now we're going to talk about being stretched and shrunk or compressed going left and right or horizontal. What that means is, even though you have some graphs that are going to look the same, that are going to kind of do the same thing as what you saw yesterday, they're actually being manipulated in a different way. It sounds really confusing, but once we take a look at it and once we compare the two, I think it'll make a little more sense. So what we still have to remember is our parent function, which is our most basic function. This is our parent function. So this is what we're going to look at and compare to all the graphs we do tonight. Just to kind of take a little visual here and think about what we learned yesterday. Yesterday, if we look at the girl there on the left, we said if we stretched her vertically, our graph got skinnier. So you can see we've stretched her, we've attached a string to the top of her head, we've pulled on that, and she has gotten a lot skinnier. We move over to the picture on the right, and we're going to shrink her. We're going to put our hand on top of her head, we're going to just push her straight down, and she gets a little wider in that mirror. But let's think about it a different way. So those are our vertical lenses. Now, I want you to think about it in a horizontal. If we have something here that pushes in on both sides, it causes our graph to get skinnier or to get bigger faster. If we have something that pulls on each side, then this part gets shorter and smaller. I have one more visual I want to show you to kind of make you think about what we're doing here. And we're going to take a look at some slime. So let's take a look at that real quick. Okay, so when that ball of slime was pulled apart, it got a lot skinnier in the middle. And when they made it back into a ball and when they pushed it back together, that middle got a lot wider. So what we can think about is, depending on the way they were pushing and pulling that ball of slime, that is the direction of our shrink or stretch. So let's go back up to the first page, and let's take a look at that again. When 0 is smaller, or let's say it like this. When A is when the absolute value of a is larger than 0 but smaller than 1, so maybe a fraction or a decimal, the graph of f of x equals a times x squared is a horizontal stretch. Remember, that means we're going to take this graph and we're going to stretch it like this, okay? What that's going to do is push all of these values down, meaning that that graph gets a lot wider. Let's change the color here. For a horizontal shrink or compression, we're going to take this graph and we're going to squish it together from the left and right, which is going to pull all of our values up. So a stretch is going to make it wider, and a shrink is going to make it narrower. The last thing to remember on this one is that the scale factor of a horizontal stretch or shrink is the absolute value reciprocal of a, and I'll talk about that a little bit more once we get into the problems. So, going on to our first one here, and I'm going to make this a little bit bigger just because that way we have more room on the graph. Actually, I'm not going to do that quite yet because I want to show you one other thing on the calculator. So we're going to look at something on the calculator because I want everybody to understand that even though our parent function is going to look a little bit different, it is the same parent function. So on yesterday's notes, we had a y equals x squared, and we had a y equals 5 times x squared. And when we looked at that graph, it looked a lot like this. That blue one is going to be our parent function. That red one is 5 times x squared. But if we look at 5 times x in parentheses and square that whole thing, that's going to be our green one. I'm going to go ahead and hide that one, the second one for now. There's our parent function in blue. As you can see, I guess it's black. The black one is our new function. And what I'm going to do so that I can see it a little better, because our outputs are getting big really, really fast, so it's really, really skinny. I'm going to hit zoom, and then I'm going to hit number 2, or zoom in, enter, so I'm right there on that center axis. Now, as you can see, our parent function looks a little bit wider, so it's going to look a little bit wider than what we did yesterday, but it is still the same parent function. So, going back to our graph, we have the function of g of x equals 5 times x squared. And what I'm going to do is graph that. I'm going to graph our parent function so we have a reference. And I think that's mostly blue. They were in blue yesterday. And we're going to do the same at the bottom. We have -1, -2, -3, -4, and 1, 2, 3, 4. But because our numbers are going to get really, really big, really, really fast, we're going to make this scale of 5s. And so on. Now going back to graphing our parent function, so 1 times 1 is 1, that should be about right there. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. So as you can see, it's going to be a lot wider than yesterday's. Negative 1 times negative 1 is 1. Negative 2 times negative 2 is 4. Negative 3 times negative 3 is 9. And negative 4 times negative 4 is 16. So we're staying up, still opening upwards, because that is our parent graph. So our blue graph is f of x equals x squared. Let's make this next one green. So for this one that we're working on, we're going to work in green. I'm going to make that a little thinner so that maybe it makes more sense. Okay, so if we were to solve x when we put in 1, we would have 5 times 1 squared equals 5. So we go over here, x is 1, we have 5. Now we're going to go ahead and see what that's going to be if we input a 2. And so 5 times 2 is 10, 10 squared is 100. Well, like I said, our numbers are going to get really big really fast, and we don't even have 100 on here, so we maybe have it way up here. And of course, when we square something, we have a positive again, because it's negative times a negative, which is what we're squaring, is a positive. And we've got negative 1 times negative 1 is 5, and then 5 times negative 2 squared is going to be 100 again, so it's going to be way up here somewhere, maybe over here. So if we draw that graph, it looks more like that. Oops, got that a little wide, sorry. So as we can see, we have done a horizontal compression. Our graph went in horizontally. We've done a horizontal compression with the scale factor of 1 over 5. Remember, if you look right above that, it says that the scale factor of a horizontal stretch or shrink is the absolute value reciprocal of A. A, in this case, equals 5. So we have a horizontal compression with the scale factor of 1/5. Whoops. I'm so sorry about that. I did not mean to erase that. I meant to move this board, but it's not going. Sorry. Okay. So if we looked at yesterday's and we said, well, we've also pulled that upwards, it looks exactly like a vertical stretch. Why aren't we calling it that? Well, that's because when we move back up to look at the equation here, right here is going to tell us when we have a horizontal or a vertical stretch or shrink. Because that 5 is being squared along with the x, it is part of that x value. And as we all know, the x-axis is the horizontal axis. When that a value is not being squared, we would say that was outside the x value. So this a is manipulating the y-axis out here. And that's how we get the difference between a vertical and a horizontal shrink or stretch. They will look a lot alike. It's just very important to understand which one is going to be which. And we're going to work through a few more so we can really kind of see that. So moving on to number 2, it looks like I'm cut off over here towards the right of it, so we might have to go down a bit. Oops, sorry about that. We have negative 4x squared. Yesterday we talked about how if you have a negative, it makes that graph open downwards. Well, it's not necessarily true in this case because we're going to square negative 4 before before we draw that graph. It's inside the parentheses. So if we go back and draw our parent function here, and again, I'm going to draw it in blue so we know that it is the same one as before. Our y-axis. It'll look a lot like the one from over there. So let's see what scale we need to do for number 2. Well, because we're doing negative 4, and we're squaring that, that's going to become a 16, we know that that's going to get pretty big pretty fast again. So let's do it on a scale of 10 since we ran out of room before. And go ahead and fill in that parent function. And as we can see, looks even a little different than the one there beside it because, again, we have a different scale. And we did that last one in green. Let's do this next one in red. So we are going to put in 1 for the value of x. So m of 1 equals negative 4 times 1 squared. And we get 16. So that's about, let's say right there. Let's try m of 2 equals negative 4 times 2 squared. And we are going to get 64. So that a little bigger. That's about, let's call that right there. And because we know that negative 4 times negative 2 squared is also going to be 64, we're going to go ahead and put that right there. We'll put that right there for now. And then if we plug in that 3 for x, we would get negative 4 times 3 squared equals 144, and that is off of our graph, so we know that this is going to kind of go way up like that, right? Oh my goodness, I'm so sorry. Way up like that. Again, because that negative 4 is inside the parentheses, it has given us a horizontal shrink or compression with a scale factor of 1 over 4. And it's not a 1 over negative 4 because it's not opening down, because that negative is getting squared, which gives us all positives. Let's move on to number 3. So now we have a negative inside and a negative outside. What that is going to do is, you guessed it, this graph is going to open down. Because that 1/5 gets squared and becomes positive, but then we have a negative on the outside, which tells us that we're going to open this graph downward. So let's draw our parent function. And because we know our parent function is going to open upwards, because remember our parent function is f of x. So if we draw, let's put our x-axis here in the middle. This x-axis here in the middle. Our y-axis. And we'll just do a scale of 1 to 1. So this is 1 right here. This is 1 right here. This is negative 1, and this is negative 1. So there we go. 1, 2, 3, 4. There we go. And we have a 1 times 1 here. And 2 times 2 would be here. So this is our parent function right here. Okay? Now, what are we going to do? I'll go back to red since I started in that over here. What are we going to do with this? Well, like I said, we know it's going to open down. So, the first thing we're going to do is plug in a 1 for x. So, r of 1 equals negative on the outside, negative 1/5 times 1 squared, which will give us a negative 0.04. Well, we're doing a 1-to-1 scale, so 1 and 0.04, that's pretty close to that line. And moving to our 2 value, we would get a negative 1/5, times 2 squared will give us a negative 0.16. So let's call that, I don't know, right about there. And I went ahead and plugged that into my calculator, so I know that a 3 will give me a negative 0.36, and these are so close together, I'm probably moving too far, but as you can see, that's a pretty, sorry, let me undo that because that was not even close to the x. That is a pretty wide parabola that we have moving downward and really, really wide. What is the most confusing thing, unless you think about your reciprocals, is that why would a 5 give us a narrower graph than a 1/5? That's because on your horizontal stretch and stretch and shrink, not slide. On your horizontal stretch and shrink, you are using the reciprocal of your a value as your scale factor. So our scale factor for this is a negative 5. I'm going to go ahead and do number 4 with you in class tomorrow so we can move on to these word problems. So this says the diagram shows the cross section of a soup bowl where x and y are measured in inches. Find, well, let's see, maybe we should do number 5 first. Sorry about that. The diagram shows the cross-section of a satellite dish where x and y are measured in meters. Find the domain of the width and the range and of the depth of a dish. This picture is a little hard to see, so what we have here is a satellite dish. Okay? The coordinates of those points are going to tell us our domain and range. So if I look at that, I can see, okay, my furthest to the left point on the x-axis is a negative 2. And then I look over here and I've got a positive 2. So I know that my x has to lie somewhere between those numbers, and it's got to be larger than or equal to negative 2 and smaller than or equal to 2. And that is our domain. Now, we can look at the same thing for our range. Well, it's going to be 1 on both sides because it's a y value, and I can barely see that's a 0 down there. So, I know that we go from 0 to 1, all of our y coordinates have to lie somewhere in between them, and it's got to be greater than or equal to 0 and less than or equal to 1, and that is our range. Going on to number 6, now we're going to look at that cross-section of a soup bowl where x and y are measured in inches. So doing the width and the depth, we're going to use the domain and the range to find the width and the depth of the bowl. If we are looking at the width, we can see that it goes from -4 to 0, and it goes from 0 to 4. Both of those are 4 units, correct? Even though one is a -4. Another way we can look at that is to take our new versus our previous. Our new is going to be 4. Not versus, I'm sorry. Our new minus our previous. Our new is 4, and our previous is -4. And as we all know, when we subtract a negative number from a positive number, it becomes positive, and we get an 8. So our width of the bowl is 8 inches. We can do the same thing here with the depth of the bowl. We see here that it goes from 0. Let's do it the other way. Our new, I'm sorry, is 2. Minus 0 is 2, which means it is 2 inches deep. And you want to make sure that you don't look at this. Well, that's, can't really see it with that color. You don't want to look at this curve right here, because that's just the curve of the bowl. If you look at a bowl, they're flat, and they end at the same place. So you make sure that you're looking at that y-axis right there. Okay, we are going to go ahead and do number 6. We'll talk about number 6 and 7 in class tomorrow, and we'll talk a little bit more about the difference and the similarities between the horizontal and the vertical stretch and shrink.